So in this video, we're going to talk a little bit about arithmetic notation, which is not really covered in the Zybook, but it's something that's going to be useful for the lab this week, and it's something to keep in mind as we're going, as you're moving on to other classes as well. So arithmetic notation is sort of what we use to communicate in math. So in probably all of your classes that you've seen, all of your math classes that you've had up until now, you've seen equations like this, nice arithmetic equations that we know how to evaluate using our order of operations, right? First we process what's in parentheses. So we add the 1 and the 3 to get 4, multiply that by 7 to get 21, or 28, and then add 4. So we know, given this expression, that it evaluates to 32, right? We know how to evaluate that. If I gave you that problem on if I asked somebody in middle school, they would know how to evaluate that. But we can go beyond that. So this is what we call infix notation, right? So this is in order, meaning the operators are in between the two values that they're acting upon. So we could, and we've left some stuff out here to make it a little bit easier for us to read, right? Because we understand that there's an order of operations. But if we didn't, if we only knew that parentheses came first, or to force a different order of operations, we could add extra parentheses, right, around the 7 and the other operator and the other value. But this evaluates the same thing. Again, you process the innermost parentheses first, and then the next, and then the outside part is again sort of has implicit parentheses, but we could draw those around here, right? So this is sort of what we've always seen as arithmetic notation. But there's other ways to write it depending on what we want to do with it. So just like we have in order, pre-order, and post-order depth first tree traversal, and we'll see how these are related later, we have infix, prefix, and postfix notation. So we talked on the last slide about what infix notation is. So here, given this example from the last slide, we know infix notation, right, puts the operator between the two things. So here, the plus sign goes between the 4 and this parenthetical. What we do with postfix is we take the operator and we move it to the back, right? Sorry, prefix, we move it to the front. So we take the plus and we move it out to the front. We say 4, so we're going to add 4, and, well, now we see a parentheses, so there's some other thing that we're going to need to evaluate. Okay, so then we go inside and we see, well, inside that there's a multiplication. We're going to multiply 7 times some other thing that we have to evaluate. So you go inside. Here we have plus, so we're going to add 1 and 3. So it's the same thing. It's just now we've decided, by convention, that we're going to stick this out front. But if I had told you this ahead of time and I gave you a new equation in prefix order, right, and said this is in prefix order, give me a number, you would still be able to figure out, first you need to add the 1 and the 3 to get 4, and then you're going to multiply that by 7 to get 28, and then you're going to add 4 to get 32, right? And I bet you can guess what postfix is. Postfix, instead of taking the operator and moving it to the front, we're going to move it to the back. So we have some value, some 4, right? And we're going to operate on a 4 and some other operator, some other value. Again, a 7 and some other value to do multiplication, the 1 and the 3 to do addition. So we can see how it would be useful in this notation to use a stack, right? We push the 4 onto the stack, and then we push the 7 onto the stack, and then we push the 3. So let's actually try that for a second. So we first push the 4, and then, well, the next thing is a 7. 7. We don't have an operation yet, so we get to 1. And we get to the 3. There's still no operation. And then we get to the plus. Well, the plus says take the 1 and the 3 and add them. Right? So we're going to remove these two and replace it with 4. And then we're going to multiply. 7 times 4 is 28. And then we're going to add 4 and 28 to get 32. And then when we get to the end, when there's nothing left, hopefully, there should only be one thing left in the stack, and that's our answer. So this infix is very good for recursion, right? Because we could say, right, you could split this off, find the operator, and split this off. Here, again, you find the operator, you split it in half. Here you find the operator, you split it in half. But postfix is much easier using a stack. So these are the three main notations for arithmetic notation, but there's another way to represent an equation that we haven't talked about yet, and that's as an expression tree. So expression trees exist without having to know an order, right? So you know that we have the final operation is some addition between 4 and something else, and that something else is a multiplication between 7 and some other thing, and that other thing is an addition between 1 and 3. And in order for you to process the addition at the top, you have to process this multiplication, or you can't do anything. In order to process that multiplication, you have to process the addition. So here, every operator has 2 children, left and a right child, and each value is a leaf. Right? 4, 7, 1, and 3. Those are the numbers in our equation that we're trying to evaluate. Right? And we can process the value at an operation if we know the value of its 2 children. Well, if it's just a number, we know its value already. If it's another operation, you have to evaluate that first, right? And in that way, the depth first traversals that we already know actually correspond to these arithmetic notation orders, right? So infix notation is the same as in-order traversal. So think about the way we do in-order traversal, right? We're first going to process the left. Starting at the root, we're going to process the left tree. Well, processing the left tree, since it's a leaf, means just printing out the left tree. Oh, sorry. And then you print out yourself, and then you print out the right tree. Well, the right tree processes its left tree first. So that's 7. And then it prints itself. And then it prints its right tree. Well, its right tree is another operation. And that guy prints its left tree first. And then itself. And then its right tree. And now we've finished. We keep going up. And this is exactly our equation. Infix. Similarly, prefix, right? Prints the operation first, plus, and then it prints the left tree, 4, and then the right tree, which is an operation, which is multiplication, and 7, and another operation, plus this guy, 1, and 3, and we're done. And that's exactly our pre-order if you go back and look at the last slide. Similarly with post-order, right? We print our left tree, 4, and then we print our right tree, which is a 7, which is a 1, and a 3, and a plus, and a times, and a plus, right? And if you go back and look, those are exactly the equations that we had on the last slide. So that means these expression trees are very useful for sort of getting around having to have, some ordering to our notation, right? And it provides this precedence in the way it levels this data. So what we can do is we can actually use the expression tree to help us convert from one notation to another. So say we're given this equation here in postfix notation, and we want to print it out in infix notation. Well, so first thing we need to do is construct our tree. Well, this is a 3 and a 7, and they're linked by a plus. And this is a 10 and a negative 9, linked by minus. And that has a minus and a negative 1. And these are linked, I should have drawn this over here, but they're all linked by a multiplication, which has plus, and has 3 and 7. This is a minus. This has 10 and negative 9. Oops. It's actually a minus. Oh my gosh. Minus, that has that, and negative 1. So if I erase that all the way, and if we wanted to write that in infix notation, we would just do, so this is the root, since I drew that funny, we would do an in-order traversal, right? So the in-order traversal comes down here, prints the left child first, that prints its left child first. So we're in two operations, prints its left child first is 3, prints its value, which is plus, prints the right value, which is 7. And now we're done with that, and we go up here. So we close the parentheses, and we print our self, so star. And then we go into the first operation, which is this minus. And the first thing it does is it prints its left child with another operation, which is a minus. It prints its left child, which is 10, and then prints itself, and then prints negative 9, and pops back out, minus, and its left child, which is negative 1. And we're done, and we're done. So what if we were to evaluate this, say, on the tree? Well, we can't evaluate this guy yet because we don't have the value at either of its children. So let's evaluate the left child first. 3 and 7 is 10. Now we need to evaluate the right child. Well, we can't evaluate the right child because we don't know the value here. So the value there is 10 minus negative 9. So that's 19. And now we can evaluate this guy. It's 19 minus negative 1, which is 20. And now we can evaluate the root. And the root is 20 times 10, which is 200. And we can see we would do basically the same thing here. This is 10, 19, 20, and 200. Right? So we can evaluate it in order. That's what we've always seen. We can evaluate it on the tree. We can evaluate it in post order if we wanted to, right? We would do 10, 19, 20, 200. Right. But that's how those different notations work, and that's how they're related to expression trees.